Students, hi, this is Mr. Bob. This video is about Newton's first and second law. Before watching this video, you should set up focus notes in your journal, and there's a digital template provided there if you'd like to use it, but I do recommend handwritten notes. After watching this video, I would say 2 to 4 days later, you should think about filling in, grouping, adding, chunking, identifying points of confusion, making your brain struggle somehow as you review the notes. Okay, and when you take this video, please avoid mindless copying. Stop and rewind the video as needed. I would actively listen, selectively write down things I hear, abbreviate as much as possible. If I give you a sample problem, make your brain think about it, pause the video. And if you're still confused, make sure you mark the points of confusion that you have and make it a point to reach out to a classmate or myself or revisit it on your own. Two essential questions. How can we apply Newton's first law to help us understand how when things change their motion? And second, how can we apply Newton's second law to help us analyze situations and solve problems? Let's back up a second. Why do objects move? This is something that has perplexed people for a long time. And if we go way back to Aristotle, by the way, there's really no need to take notes on this slide, but it's a good context. Aristotle basically said the natural state of motion of all objects, but the heavenly ones, is one of rest. And so if you're a child and you push a wagon, as you can see there, eventually it'll stop if you stop pushing it. So the child might reasonably conclude something like this: you need a force to keep something in motion. And I suspect some of you either consciously or subconsciously have that idea in your head or have had it in the past, or maybe you still currently have it. But as we've come to learn and will continue to learn in this class, these observations are not adequate in many cases, okay? Galileo came along at some point and he basically said, let's say I'm shopping at Trader Joe's and I take my shopping cart. Galileo shopped at Trader Joe's, I heard that. If you give the cart a push on a smooth level surface, eventually comes to a stop, similar to what the little boy or the little child with the wagon. But Galileo went further and thought, what can I do to increase that distance that it moves? He thought, if I can minimize friction, it'll go further. So he got out his oil can and oiled those wheels and sent it along its way, and it went further. And then he basically took this idea all the way and he thought, if I could take away friction completely, entirely, not just minimize it, but completely remove it, any sort of friction or air resistance or drag, something would move forever as long as I just gave it an initial push. Okay, so the key breakthrough he made here is not to understand that you need to put a force on something to keep it moving, but his key idea was this idea of inertia. And inertia suggests that once something has a certain state of motion, either sitting still or moving in a constant velocity in a certain direction, then it will continue to keep doing that unless it feels an external force. Okay, and he called this idea inertia. He said all objects with mass have inertia, and inertia is this tendency for an object to resist changes in its motion. Okay, so this inertia word is really important, and it kind of gets at the fundamental shift in our thinking that we needed to have several centuries ago. Okay, and there you go, cart goes forever. So Isaac Newton comes along, and he basically formalizes this, what Galileo is saying in his, what he calls his first law, and it's also known as Newton's law of inertia. And he basically says this: the velocity of an object will not change if there is a net force, or excuse me, will only change if there's a net force acting on it. The velocity of an object will only change if there's a net force acting on it. In symbols, we could write it this way: the sum of the forces acting on an object, if those add up to 0, then the velocity of that object is going to be constant. Okay. So there you have it in words, there you have it in equation form. Let's go on to Newton's second law, but first, a joke. What sport makes toes cry? Football. All right, Newton's second law. Newton's second law basically is an equation. It's a very important equation, sometimes misunderstood. It says that the net force, or the sum of all forces acting on an object, is equal to that object's mass times its acceleration. I like to think of it this way. Okay, the acceleration of an object depends on two things: the net force it feels and how much mass it has. And the bigger the net force, the bigger the acceleration is going to be. The bigger the mass of an object, the smaller the acceleration if everything else is the same. So that's Newton's second law. Now we can make this, and we will make this equation specific for a given direction. As we've talked about before, motion in different directions is independent of each other. So for example, net force in the x direction equals the mass of the object times its acceleration in the x direction. And similarly, independently, the net force in the y direction equals the mass of the object times its acceleration in the y direction. Just a couple more notes about Newton's second law, really important for solving problems. Remember, if the acceleration is 0 in any direction, then all of these things are true. The sum of the forces has to be 0 in that direction. The net force in that direction has to be 0. And the velocity in that direction has to be constant. These are all important things to remember and very key to remember when you're analyzing problems, solving that sort of stuff. All right, a couple of vocabulary terms I just want to talk about very quickly because you'll see them from time to time and they tend to confuse students sometimes. Big words here, translational equilibrium, okay? Equilibrium, the word equilibrium means kind of balanced, right? So if the forces are balanced, then the sum of all forces is going to be 0. And that's going to be true in all three of these cases. So whenever you see the word equilibrium, immediately think, there is no net force. Sum of all forces have to add up to 0. Okay, and then the difference in each of these scenarios is what sort of velocities they describe. Okay, so static, if something is static, that means it is not moving. So the velocity equals 0. The word dynamic seems to imply that something is moving. So this would be velocity does not equal 0. Okay. And then translational equilibrium is kind of the umbrella of the two. Translational equilibrium, if something is in static equilibrium, it's also going to be in translational equilibrium. If something is dynamic equilibrium, it's also in translational equilibrium because translational equilibrium means any velocity. So as long as the sum of the forces is 0, an object can have any velocity and we can say it's in translational equilibrium. Another way to think about it is that translational equilibrium is like the parent category. Okay, and then underneath it, it has two specific subcategories for more specialized. One would be static equilibrium, and the other would be dynamic equilibrium. You could consider it like produce, right? If you go to the grocery store for produce, there's fruits and there's vegetables. All of it's produce, so the fruit might be the dynamic equilibrium, the vegetables might be the static equilibrium, and produce is the translational equilibrium. Okay, so that's it. Hopefully you have learned how to apply Newton's first law to help us understand how and when things change their motion, and you can apply Newton's second law to help you analyze situations and solve problems. Thanks for listening.